Okay, let's carry on. Next step is to prove Grothendieck-Riemann-Roch for an embedding. X included in Y cross P another thing, but basically X included in Y for any non-singular Y. But instead of looking at a general embedding, it turns out it's easier to first look at a special kind of embedding and then compare the special embedding with the general one. This deformation to the normal cone will be involved here again. So what we do is we look at the following special type of embedding. So let X non-singular E locally free of rank R and what I'll do is I'll let Q be the projective bundle of E direct sum or trivial line bundle, which is going to be proj of the symmetric algebra or OX of E dual direct sum OX. That's our notation. So this is an example of a projective bundle. But let's notice there are various things we know about this. One, there exists an open subscheme J E included in Y with complement the closed subscheme I P E included in Y associated to the surjection sim dot E dual direct sum OX you have a surjection of graded sheaves of algebras. There's a map the other way in proj, and this is a closed embedding. That's so this is the thing which we had called PE with a single P, and this is P of some bigger E prime. So you have this. Well, this came from the surjection E dual direct sum OX onto E dual. But of course, I have another surjection E dual direct sum OX onto OX. The surjection gives another closed subscheme, an embedding I guess I'll call it X from X, which is just the proj of the symmetric algebra of OX. If you take the polynomial ring in one variable OX and take its proj, you've done nothing. You've taken the same space X. So I'll call that S X to Y. Let's notice some other properties. So of course this is also a section in the sense that if I take Q, the composition is the identity. Right. And let's observe some other properties. The kernels of the two surjections which I started with, E dual direct sum OX onto E dual and E dual direct sum OX to OX give me, of course, kernels on the level of symmetric algebra, the two ideals, and those two kernels together span this vector bundle. But This is the direct sum of two things. I took the two pieces, of course they span. But then if I think of it at the gradient level, that will say the ideal generated by the kernel on symmetric algebras here and the kernel of the symmetric algebras here, it's not the unit ideal, but it's the irrelevant ideal. Right? It's like the irrelevant maximum ideal in a graded ring. So when you take prod, that's the empty set. This implies, therefore, that S of x intersection I of PE is the empty set. And if I have two subschemes given by two ideals in a graded context, and the ideals together generate, well, not the unit ideal, but the irrelevant ideal, that's good enough, or even the radical generated would have been sufficient. So this is correct. Therefore implies that Sx is actually contained in the open E contained in Y. So I'll let Se x to E denote this map. So S is formally J composed with Se. Now, as I first include the x into E and then include E into Y as an open set, the composition is the original, is the closed embedding. Okay. And of course, then I also have Q restricted to E from E to X is the what Hartshorne would call geometric vector bundle associated to E. SE is its zero section. So now that I've got two embeddings, if you like, I have an embedding of X inside the open E. Open E is a vector bundle over X, and this is the zero section. Or Y is a projective bundle which happens to have a section in particular, and that section is S. It's the same subscheme, but I'm thinking of it as sitting inside two different ambient things for calculation purpose. I'll need to, fiddle with the various embeddings to do things. So in particular, in the end, you have a diagram of the following kind. E, Y, PE, X. I have what I think called pi here. This I'm now going to call little p. This I'm calling Q. Going up, I have S. Going up there, I have S. Okay. Just to keep track of all the things and where they're sitting and where they're mapping, I need letters. I do various calculations. Looking at that. Which one? Which horizontal map? I didn't write J. I. Thank you. Every one of those maps I'll have to use in calculations, so it's good to have some letter associated with it. I should try not to erase this picture until I finish the calculation. Let's see. Since E, remember, was Y minus PE, there's an exact sequence of Chow groups which must have been constructed earlier in the course. Every degree k, I can take the Chow group of dimension k cycles, go I lower star, there's a J upper star is restriction to the open set. This is a standard thing. By the way, for various kinds of arguments with cycles doing inductions, it's natural as what comes to the left. That's where the higher Chow groups and things come in. For example, Nitin was asking me some question earlier about local triviality and homotopy invariance and things. The natural proofs will involve all the terms to the left going out to infinity. There will be the so-called higher Chow groups. So higher Chow groups are there in order to, this is only the lowest part of the sequence. Anyway. but they're less elementary. This is something we can do directly. All right. Okay, now I want to use all this setup to take the particular example of a closed embedding S, X, and Y, and I want to prove G, R directly for this. That's the plan. So basically, I'll compute everything possible, and then write it all out, and it'll work. That's going to be the game. So let's start with some proposition. For this particular S, yes, this one, which I've constructed here within that diagram. For that one, I'm going to prove it. And then the idea is that general embedding of anything in anything else, I'll attempt to compare with an embedding of this kind for the correct choice of E and so on and so forth. That's going to be deformation to the normal cone. Let's start with various calculations. Let beta in chow k E. So basically, I want to set up all sorts of formulae in calculus. After that, I'm in a position to write out the Grothendieck-Riemann-Roch thing which I want to check. And my earlier calculations, whatever they are, will be allow me to do manipulation and then prove the result. Okay. So I'm just setting up many preliminary things to start with. So let beta in chow k E, beta bar in chow k Y with J upper star beta bar equals beta. And by the exact sequence I wrote here, there are lots of such beta bars, but they may be not unique. The non-uniqueness comes from here. Okay. Then the claim is, I forgot to say something, sorry. I'll come back to this in a second. Okay, let me just write the statement, but I'll come back and explain what I'm doing here. Then SE upper star of beta is equal to Q lower star of CRE cap beta bar. Now, this symbol SE upper star has not been explained here. Of course, people have talked about Jizen maps and induced maps on cycles associated with that, so that's a general theory. But here I'm going to just do it by hand explicitly in my example. But it's also an example, a special case of what one knows in the general theory. How to construct such a map SE upper star. Well, the point is here I'll use the following fact that I know certain theorems already about Chow groups, which other lecturers have proved. I'm just going to write down those statements. The flat pullback maps pi upper star from Chow k minus Rx to Chow k E are isomorphic for all k. So in particular, I get that Chow k E equals 0 for k less than R. This is the sort of homotopy invariance property. This must have been proved in the earlier lectures for sure. And second, I need a version of the projective bundle formula. Each beta in Chow k PE is uniquely expressible as beta equals sum I equals 0 to E C1 O PE of 1 to the I cap P upper star alpha I. Now I've changed the notation. Pi was something else. P is this map, the projective bundle map. So the projective bundle formula says, one way of saying it is that the graded Chow group of P is a free module, so to speak, over the graded or the Chow ring of the base, which generates one zeta squared up to zeta to the something. And that's exactly saying that every element is expressible as a pullback of classes times powers of the thing. So this is projective bundle form. Okay? This has been proved. Okay. So as part of this, I get therefore that pi upper star chow k minus r of x to chow k of e is an isomorphism. So there is an inverse isomorphism. This inverse isomorphism I just call SE upper star. That's the definition for me. SE upper star is the inverse of the natural isomorphism coming from homotopy invariants. Okay, just to be very expert. Okay, now what can I do with that? So at least now in my proposition or whatever here, both the sides are defined.
R is your rank.
R is the rank. R is the rank. Yeah, that was part of the. I just erased that. And maybe, if convenient, I might end up writing it as E plus 1 for some other number E. If I want to talk about segregate classes or things of that kind. So for example, E is written in the sum. Yeah. One more thing I have not explained here, the formula. This I wrote CRE, but I think I made a mistake here. I do not want to write that. I want to write CRQ. And what is Q? Q is defined by universal exact sequence, and so to speak, universal exact sequence O PE of minus 1 goes to, I can't take this, but I don't want to do it. I want to do something else. 0 to OY of minus 1 goes to Q upper star of E plus OX goes to capital Q goes to Z. So remember, Y was the topmost thing. Y was proj of sim of E dual plus O. Right, so there is such a universal sequence on Y, and therefore I have this diagram. So now Q is a vector bundle on Y, and so I can, it has rank R in fact. This has rank R plus 1, and this has rank 1, so that has rank R. So I'm talking about the top joint class of that Q, and then I'm asserting that the action of that on beta bar pushed down to X is the calculation for this SE upper star beta. I asserted there is a map SE upper star, the inverse isomorphism. I'm giving you a kind of formula for it. I'm saying take a class here, in order to compute what it is, so to speak, close it up in Y, apply the top joint class of that Q, and then push it down from Y to X. And that's the answer. That's what it's saying. So let's check that. So for proof, I need to show that pi upper star of Q lower star of CR Q cap beta bar is equal to J upper star of beta bar. For any beta bar, this is what I want to prove. I claim this is entirely equal to this equation. Okay, I just said that. Take beta, find something which is on the whole space which restricts to beta, and then apply the operation to that. The SE upper star by definition was the inverse of something else. So I can put SE upper star inverse on the other side and then it becomes the other map, and that's what my formula is. So this is what I have to prove. This is exactly the restatement of the formula written there. Let's try to check it. The point is I can write beta bar, and this decombination is in fact unique. Q upper star of some gamma plus I lower star of some delta with gamma in chow star x in an appropriate degree and delta in chow star of PE. That's because I have a formula for writing a general element beta in some fashion. Or put a different way, I can say I can use this, the quickest way perhaps is to use this exact sequence. Anything here is basically governed by what was here plus something coming from here. The things which are living there are the ones which pull back from below. So general elements are things pulled back from below, which covers everything here, plus stuff coming from there. Right? So that's just saying this. So now I want to claim, then I claim two things. Q lower star of the first term that the first term in fact just recovers the gamma I started with. And the second term I'll claim gives 0. I'll justify it in a second. In fact, even before I take Q lower star, I claim CRQ intersection I lower star delta is already 0. So I don't even have to take its Q lower star. This I can easily justify. This is clearly equal to I lower star of CR of I upper star Q intersection delta by projection formula. But let's take our big exact sequence there and restrict it to the thing at infinity. You find, I should have argued something here. No, I have to do it carefully. I don't use the exact sequence, I use something else. I noticed something else also about Q which I forgot to write, and this is a slightly tricky thing. Where is it? Yeah, I've got Q here. Notice that Q comes equipped with a global section. I took here a vector bundle which is the direct sum of another vector bundle plus a trivial line bundle and pulled it back. So the trivial factor is still there upstairs, and then its image in the quotient is there. That's a section. This has 0 scheme SE, SX. This is what I claim. Now this I think is, I'll leave you to verify it. There are various ways you can check this. So what's the definition of the 0 scheme, right? OX maps to Q. So there's a dual exact sequence, Q dual to maps to Q upper star of, sorry, this is E dual I think, right? Is that right? E dual? No, this is E. So here I have E dual, I think. Oh yeah, here I have to have the dual. I'll have such an exact sequence, right? And from here I have a projection to OY, which is the Q upper star OX. Right? There's a projection to that summap. Therefore, the map like this. This maps to some ideal of something. So I claim it's in fact the ideal of Sx sitting inside this. Okay? This is what I assert. This claim you are saying 0 scheme means this property must be true. I'm not going to check it. Please work it out as a Of course, there are different ways of doing this exercise. You can go to open sets and patch and do things, or you can directly work with sheaves of modules. Q dual here is given by some exact sequence. This comes from some graded sheaf of modules. This comes from another graded sheaf of modules, graded map. Compute term by term. You'll get some sort of formula for the graded kernel. Calculate everything. You will in fact get the natural graded ideal here. If you work everything out, you'll get the correct. But you've got to do the computation and satisfy yourself that it works. Okay? It's doable. Of course, you can work with local coordinates, or you can restrict to an open neighborhood, and there it looks. There are different types of arguments. It's a good exercise in projective jugglery to try to directly compute the graded ideal obtained from this picture and check that it is the correct ideal. Sx is given to me explicitly. I've got a quotient of the symmetric algebra. So therefore, I have a graded ideal in the kernel. Term by term, it will agree with the graded image after some work which you have to do. You have to stare at it. It's not. It took me also. I of course know it's correct, but I just sat to try to work it out myself. It gave me more trouble than I expected. Maybe I'm just rusty with these computations. But in any case, okay, let's hope that diagram is sufficient for us to manage. In any case, I claim this. So, if we know this property, then if we restrict the bundle Q, and I wanted I asserted that this expression here itself is 0 is what I wanted to prove. Right? That means I took the bundle Q and restricted it to that PE sitting inside Y. I took Q, the bundle here, and restricted it to that thing. But I'm saying the vector bundle Q, the global vector bundle, came equipped with a section whose zeros lie entirely inside this E. Namely the 0 section. Remember, E was a kind of geometric vector bundle. SE of X is a copy of X sitting here and therefore sitting inside Y. That's disjoint from that. Therefore, after restriction, the vector bundle Q comes equipped with a nowhere vanishing section. So, if a vector bundle has rank R but it has a nowhere vanishing section, then it's like a vector bundle of rank R minus 1 as far as Chern class theory is concerned. So, CR is actually equal to 0. The Chern class itself is 0. Once it's 0, of course, product with anything is 0. Okay? So that's why this term is 0 for trivial rings. Trivial meaning, from the geometry we've arranged that the Q came equipped with some sort of section. Q itself is not so easy to describe. It's described indirectly with some exact sequence. It gave a section, but the section had the property that its zeros was somewhere, and therefore when you restrict somewhere outside the zeros, the Chern class becomes 0. Right, now I want to check this. How do we do that? Yeah. Now I look at the exact sequence defining Q to try and figure out another expression for the Chern class, top Chern class CR of Q. I find that from the exact sequence, CR of Q is expressible as sum j equals 0 to R, C1 of OY of 1 raised to the power j, CR minus j of Q upper star of script T. You may be wondering why didn't I get any minus signs? Because after all, Q is the quotient, so the total Chern class of this is the ratio of this total Chern class by that one. But this is a line bundle, and I've got a minus. 1 upon 1 minus something is like 1 plus C squared, which is why everything is plus. Okay? I'm saying the fact Q, the total Chern class of Q is the ratio of the total Chern class of this and this. The term coming in the denominator is like a geometric series. Therefore, when you expand it out, you will get this with plus signs everywhere. Okay. So now let's try to do a projection formula count. Q lower star, CRQ intersection Q upper star gamma. Remember, this is Q upper star or something. That's what I want to use. is equal to, I claim it's just one of the terms will contribute, Q lower star of C1 OY of 1 to the R times C0, which is just Q upper star. Of course, I'm applying this to this. So C0 would have been just 1, so there's no term there, it's just the full O1 to the R times Q upper star gamma. I mean, if you want cap Q upper star. Plus some other terms. But if you think about it, this is the 0th Segre class. And these are the negative Segre classes. Those were the Segre classes. You take the O1, take powers of it, apply it to Q upper star or something, and then take Q lower star again. Those are the Segre classes of that appropriate vector bundle of which I took the projective bundle. Vector bundle is some whatever, this vector bundle. But we have already proved the 0th Segre class is the identity and negative Segre classes vanish. So that's exactly what I want. This is equal to gamma. That lemma, that result is proved. That formula is proved. Next thing I want to do is I want to, in an ad hoc fashion, define a Gisin map, which will, in fact, after the theory, coincide with the one developed in other lectures, but I can do it in an ad hoc fashion for me. This intersection of the section Sx is just terminology right now. I have to give you a definition of the map. Of course, such intersection has been defined and various properties have been worked out by methods, but I can do everything ad hoc here, is what I'm trying to do. I'll just define S upper star is equal to Se upper star, which I already defined, composite J upper star. This goes from chow K Y to chow K minus R over X. Now, if I want to think geometrically about what it means to intersect with that zero section, I can first pass to a neighborhood of the zero section and intersect it there. And in that neighborhood, I have homotopy invariance. So I have some understanding of what it might mean to intersect the zero section. I've just defined intersection with the zero section as the inverse of the natural homotopy isomorph. But now this thing with this definition, I want to prove an identity or two. So lemma Se upper star of composite Se lower star of alpha is equal to Cr of the locally free sheaf E intersection alpha for all alpha in tau star x. Another one of these intersection calculations, let's do it. Se upper star by definition was inverse of something. So to prove Se upper star or something equal to something else, I have to, on the other side, do a pi lower star or something. So proof, if beta is Se lower star of alpha, let beta bar be just S lower star alpha in chow, let's say, chow star of Y. Then J upper star of beta bar is certainly equal to beta. I'm just saying I have a class beta, class alpha living on the zero section. If I push it forward to the full ambient space and then restrict it to the open set, that's the same as just pushing it forward to the open set. If you want to be very pedantic about it, it's an example of compatibility of proper push forward with flat pullback. I mean, it's a very special case of that, restricting to an open set. It's sort of obvious. But the point is, if I want to compute SE upper star of something, I have to write the thing as restriction to the open set of something else. That's what the formula there said. So I can use that. Then I get that what you do is you write your original alpha, which was in, I conclude therefore that SE upper star of beta, which is the thing which I want to compute, SE upper star, SE lower star alpha, is Q lower star of CRQ intersection alpha S lower star alpha. And this is my beta bar. This was my beta. That in turn, what do I do? Let me just think. Yeah, of course. Then I can, this is some CRQ intersection cap S lower star or something. So I can do a projection formula with an S upper star and an S lower star. So this is Q lower star of S lower star of S upper star. So then I can put that inside the CR. Right? That's just projection formula. But this is the identity. Q, S was a cross section of Q. The composition is the identity. So my formula here was CRE cap alpha, and here I got CR S upper star Q cross alpha. But now, is there any difference between them? If I restrict everything to the zero section, which is what this S upper star is doing, it should somehow be obvious that, remember OY of 1 had a section coming from the hyperplane at infinity, right? So restricting to the zero section, which is in the complement, this becomes the trivial bundle. So S upper star OY of -1 is isomorphic to OX. And therefore, when I restrict everything, pull everything back under S, the Chern class of Q pullback are the same as the Chern class of E. That's why the formula here had E instead of Q. So this is the proof of this particular level. Okay. Bear with me for a bit. One has to go through some of these computations. Once we've got the right calculus set up, then the actual Riemann rock will be very smooth. One more identity I think I need. So lemma. S lower star composes S upper star alpha is equal to CRQ cap alpha for all alpha in chow star of Y. So this is saying take any class in the chow groups of Y, restrict to the zero section, whatever that means. I've defined an operation S upper star. I'm thinking of it as intersecting with the zero section. So intersect and then push it back into the ambient space. That's the same as taking the product with the top Chern class of the bundle. This is one of the fundamental, this type of identity is one of the fundamental identities related to embeddings. And in some version or other, it would have been done in the other lectures too. But here, with my ad hoc thing, I can just do it by hand. So let's do it. Proof. Write alpha equals Q upper star gamma plus I lower star delta with gamma in chow star X and delta in chow star P. S upper star decrease the dimension. S is the zero section. So of course this is linear, and I claim S upper star of I lower star is equal to 0 for obvious reasons. If I have any class here and I push it forward, S upper star is obtained by first restricting to E and then doing something, but already restricting to E gives me 0. It's part of this complex here. If I take a class here and go here, and then restrict to the open set, of course this is a complement, so of course the composition is 0. So already restricting to E is 0. So the first operation already made the element 0, therefore S upper star makes it 0. So this term is fine. So I only have to look at that one, as usual. So want S lower star S upper star of Q upper star of gamma equals CRQ intersection Q upper star of gamma. Further reduce to the case gamma is just the class of X itself, by usual projection formula games. So then Q upper star of gamma is just the class of the total space Y itself. So the question is, what is CRQ intersection the class of Y? Cap the class of Y. I claim, in fact, this is in the image of S lower star dimension of Y is R bigger, and capping with CR reduces the dimension, so it comes back to the dimension of X again. So I want to first of all claim this is in the image of S lower star. I'm actually trying to say S lower star of it is equal to that, but I'm actually saying it's in the image of S lower star. Let me first argue that. That's because, remember, Q has a global section with 0 scheme Sx. So CRQ restricted to Y minus Sx, CR of Q restricted to Y minus Sx is 0. Q is a vector bundle of rank R, and on this open subscheme, it has a no vanishing section. Okay? I removed this set of zeros. So that's true. But then remember, I have a standard exact sequence, chow dx, S lower star, chow dy to chow d of y minus sx. Correct. So I'm given sort of CRQ, cap y lives here, and it goes to 0 here. Therefore, it must come from here. But this is chow lower d of x, where x is d-dimensional. So as usual, this is just z times x. Well, z times sx, I should say, because it's s lower star. So I wanted to get in my formula there that s lower star of x, so to speak, is equal to CRQ cap y. This is what I'm attempting to prove in the lemma now. I've reduced the proof of the lemma to this special computation. And what this general argument argues is that it's at least true up to some integer m. And the question was finding out whether this m is equal to 1 or not. But now I can, whatever the equation is there with the m. Apply Q lower star. And there was that earlier lemma which was somewhere here, which this one. I know how to compute Q lower star of it. That's the thing which I started with from below. That is correct. Therefore, the m must be equal to 1. So all these other calculations are in order to be able to get this formula, which is what I need for Riemann rock. In any case, I believe some version of this formula with other definitions for the maps has been proved already with all the properties by much fancier methods. But it's nice to see you can just do it by hand. Now finally, I want to prove GRR. All this was preliminary for proof of GRR for S, X included in Y, a direct calculation. Here I noticed that I did point out this key thing which I said is true, and I suggested people might find it an interesting exercise to verify this. This Q came equipped with a global section whose zero scheme is exactly this Sx inside Y. So, this is a subscheme of codimension R in Y, which is the zero scheme of a section of a rank R locally free sheaf. Right? So, in other words, I know that there is a surjection Q dual onto the ideal sheaf of Sx. Right? Or put a different way, I can write a quotient and then now this is built for a causal complex situation. So there is a resolution and then finally the last term should be exterior R Q dual because Q had rank R. So there is a causal complex resolution.
Can you repeat what you said about inequality 1 here?
Because I applied Q lower star and then I applied this lemma, this calculation. Well, I applied it in the particular case which I anyway checked somewhere. Yeah. So now suppose F is locally free on X. Then I have Q upper star F locally free on Y. And Riemann-Roch would attempt to understand something like this: churn on Y of S lower star of F. Right? The point is, I have a proper map. I have churn. I have the sheaf map F, the lower shriek, whatever it is, and then I have its churn. And on the other hand, I have churn before doing anything and taking the star of that. And we're trying to compare those two things. Let's just compute what this is. This, if you want to be more pedantic, is churn on Y of S lower shriek of the class of F, where S lower shriek was this map from K0X to K0Y. It's one of the things appearing in Riemann-Roch. I mean, I'm just trying to say what I'm computing this because it's the same as this. Or rather, I should have written the other way. This is what I would start with in Riemann-Roch, but I quickly get rid of this and rewrite this more familiar looking object. And notice that this sequence can be tensored with Q upper star F. And I'll get a resolution. Let me put it like lambda dot of Q upper star tensor little q upper star F resolves S lower star of F. There's an exact sequence like this obtained by just taking this causal resolution, taking the vector bundle, pulling it back and tensoring it. Of course, pull it back and restrict it back to the zero section is doing nothing. That's why I wrote it. So now churn character, of course, therefore gives me some expression. So I find that this is equal to sum p equal to 0 to r minus 1 to the p churn of on y exterior p of q dual times churn y of q upper star f, which from our lemma of Grothendieck-Borel set is the same as CR of Q times Todd on Y of Q inverse times CHY of Q upper star. And this is this lemma of Borel's hair, etc. This is equal to, well, CRQ of something, we just argued, is the same as S lower star, S upper star of the thing. So I'll rewrite this as S lower star of S upper star of whatever's inside, which is Todd Y Q inverse Q upper star churn Y of churn X of F. Because I've used that churn is functorial for the map Q, so I'm able to write it like this. And what is the point of this? This S upper star is the composition of two things by definition. So let's do that. So this is equal to S lower star of SE upper star or J upper star of Todd. Sorry, there's no J upper. SE upper star or J upper star or something, but J upper star is Todd is restriction to the open set E. So let me write it like this. And then restricting to the open set everywhere allows me to replace the compact Y by the open E. I'll be left with something like this. The thing is, what is S upper star or something, right? It's first restricting to the open set and then taking SE upper star. No, that's okay. But somehow what I'm saying is that this expression here is the same as this. I've just written that as though it's obvious. This is okay, but why am I allowed to put in a J upper star? My mistake is my own confusion. It's S lower star of S upper star of this expression. That's why I was getting in trouble. It's S upper star of the whole thing. That's the point. Which is of course the same as first applying J upper star and then pi SE upper star to the whole thing. J upper star, of course, it is compatible with the product. So then I'm allowed to put the J on that side and make it pi, and I'm allowed to do this much is allowed. And now I also look at this exact sequence, 0 to OE to pi upper star E direct sum O X to J upper star Q to 0. This is the same remark I made earlier, that after restricting, removing the hyperpolarized infinity, I've trivialized the O1. So I get an exact sequence like this. So the churn classes or any characteristic classes of this are the same as the characteristic classes of this. So once I've gone to the open set, I'm allowed to replace Q by E. So then what I've got from here, therefore, is equal to S lower star of SE upper star of pi upper star of Todd X of E inverse pi upper star of churn X of F. So what I got is that this is equal to this. But this is the identity, because the pi upper star can be put there instead. Sorry, this is This is S upper star, so to speak. Hold on. What is the upshot? What do I finally? I claim this is what I will finally get. I claim that whatever proves the following. Let me write it down, then we'll stare at it for a second. Churn of S lower star F is equal to S lower star of, this is what we want, yeah. Tod X E inverse churn X F. Yeah, that's what I proved. Indeed, this is what I want to get. That's what I'm trying to do. I have the churn character, I have S lower star, and I'm trying to commute them. I have commuted them up to multiplying by Tod E inverse. That is exactly the statement of Grothendieck-Riemann rock. Except that there I said something of the tangent sheaf. Here I wrote something. So that follows from this exact sequence, 0 to Tx goes to S upper star Ty goes to E to 0. Because the space was, so to speak, obtained, I mean, here I wrote Ty, but I can as well think of this as Se upper star of Te, so to speak. So E is a vector bundle, X is its zero section. The normal bundle of the zero section of a vector bundle is the same vector bundle. That's what this exact sequence is saying. Therefore, this Tod term is the ratio of the Tods, which is what I would want in the Riemann rock theorem. So I have proved GRR for this summary. This case is done. Okay? So, in a sense, some key point is this formula, more or less, which I managed in some ad hoc fashion here, including the ad hoc definition of S upper star. But in a more sophisticated way, the theory has also been developed by other lecturers, and they have proved various formulae which give me the same conclusion. So the point is, once you've got that, and you've got the resolution, the geometry immediately produces the Riemann rock for free, and it sort of explains the Tod class also as the ratio of the class of the causal complex by something, by the top churn class. The top churn class is almost equal to the total churn character of the causal complex, but it is up to a unit. And that extra unit is the Tod class. Okay, now let's get to GRR for a general embedding. That's surprisingly not so difficult now. Maybe, I don't know, surprisingly or not. You've seen deformation to the normal cone a few times. It's a beautiful idea, and it takes care of all sorts of technical difficulties. Sorry?
Why is beta equal
Prove it. Spec of a symmetric algebra of a locally free sheaf includes the zero section. The omega is the dual locally free sheaf, is the way to say it. The sheaf of Kähler differentials is the dual sheaf. You have to. Oh. No, I'm saying it is exact with the normal sheaf, whatever it is as the quotient. But I'm saying in this example, you will find that it's actually the sheaf E. Because it's the scheme is itself a vector bundle. So think of the case X is a point. I'm saying the tangent space of tangent sheaf of affine space is the trivial bundle. Right. So now I want GRR for a regular embedding. F X into 1. So since I have a regular embedding, in other words, X and Y are for me non-singular varieties, and Fx to Y is a closed embedding. I have an exact sequence 0 to Tx to F upper star Ty to the normal sheaf n to 0. There exists a locally free sheaf, a normal sheaf, which fits into this exact sequence. So what I do is I look at F bar. I look at the scheme P of script n direct sum OX. This is like P of script E direct sum OX in our earlier thing, so it's very similar. So remember that had a zero section. So now this also has a zero section. I'll call it F bar, the zero section. And so N plus O corresponds somehow to E plus O. And then also I have the other things. I had the capital E at this level, which is the geometric vector bundle. So here also I'll have a capital N, which is P of N plus OX minus P of N. And this is spec of sim and dual. So what we do is deformation to the normal cone. M equals blow up of y cross P1 along x cross infinity. And let's notice that x cross infinity is x cross P1 intersection y cross infinity, where this is a smooth Cartier subvariety. And this intersection here is transversal. Just noting various points, so then I can just read off various properties of deformation to the normal cone. I think now I can erase all of this stuff. I need another similar diagram in a bit. I claim various standard properties that follow from this geometry. Strict transform of x cross P1 is blow up on x cross P1 of a Cartier divisor so is canonically isomorphic to x cross P1 itself. So let capital F x cross P1 to M is a corresponding embedding. This is a new regular embedding. And the second point is y tilde equals strict transform of y strict transform of y cross infinity is disjoint from f of x cross P1. Well, I had these two things which intersected transversally and I blew up the intersection. So of course, when you blow up two things meeting transversally and blow up the intersection, they become disjoint in the block, which is what you're saying here. And third, the normal sheaf of x cross infinity in y cross P1 is n direct from OX. So the exceptional divisor of M to y cross P1, the blow up which I started with, I blew up along some locus, smooth locus. So it the exceptional divisor is like the projective bundle of the normal bundle of that locus. So is identified with P of n plus y. And then I have the fibers over 0 and infinity and so on. So let's go over that also. As the fiber over 0 is just naturally y itself, I haven't done any blow up near 0. And fiber over infinity, well, the exceptional divisor is there. And there's the strict transform, and I claim the union is over Pn. This is the fiber over 0 and this is the fiber over infinity. It's the union of these two things. They meet in this fashion. And then I have various morphisms. For example, I have K, the inclusion of P of n plus OX in M. I have L, the inclusion of Y tilde in M. And I have J infinity, M infinity containing M, J0, M0 containing M, or Y to M, I can say. And then in the end, I have a big commutative diagram. If you write it down, yeah. M0 is Y. I just rewrote it as Y, yeah. So I have a commutative. Actually, the diagram should have had some more arrows, but my tech powers sort of failed at this point. XY pick has been renewed, I found. The new macros, I couldn't figure out how to put an arrow going all over the place. Anyway, it doesn't matter. Most of the arrows are there, so I hope this is sufficient for the diagram. Let's see. Let me call it little left bar. Oh yeah, that was this little left bar here. Sorry. This was J infinity. This was K, I think, yeah. We have at least this and little more. We also have Y tilde here. This map I'm calling L infinity, and I intended to put another map like this, which was supposed to be L, and I was unable to put that into my diagram. Just put it in pen. Okay. Now let. Yes. 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 Of course, when you do the tech, it straightens out all the things, makes these arrows vertical. When I'm doing it on the board, I'm afraid it's getting a little homotopy modified. Okay, now the claim is once you've written everything down, the actual proof is obvious. So I start with F locally free on X. Alpha its class. And then I consider P upper star F. With class is P upper star alpha on X class P. And then I can look at F lower star of P upper star F on M. This is some coherent sheaf on M. M is non-singular. It has a resolution by vector bundle. Let's just take one. Choose one. Fix resolution. Zero to Gn minus 1, G0 to F lower star P upper star to 0. This is on M. Then I claim various things happen. One, if I restrict to M0 via J0 upper star, get J0 upper star G dot mapping to F lower star F to 0 resolution by vector bundles on Y. Next, restrict to M infinity. Sorry? Little f is the original embedding I started with. No? Fx to y I started with something. F bar was the one parameter version of it, which at every time t not equal to infinity is the original embedding x equal to y, and at t equal to infinity is the embedding into that p of the normal bundle of something. That is the deformation to the normal cone, right? I mean, everything outside the normal cone is the original embedding, constant thing. So restrict to M infinity, get resolution of F bar lower star F by vector bundles on M infinity, which remember was the union of P of n plus OX direct from Y tilde. But F of x cross P1 intersection Y tilde is the empty set, and the support of our sheaf is capital F lower star or something lives here. So the sheaf which I am resolving by vector bundles doesn't have any support at all on this. So I took the exact sequence of vector bundles and restricted it there. I'll get just, I mean, the restriction of this thing is 0, and I'll just get an exact sequence of vector bundles. And on the other hand, if I restrict to the other side, I'll get a resolution. So I get that K upper star G dot to F bar lower star F resolution on P of n plus OX and L upper star G dot, an exact sequence of vector bundles. On Y tilde. And now let me just compute and I'm done. I'm interested in J0 lower star of churn Y of F lower star F this J0 lower star churn Y of J0 upper star G dot I can do this as churn M on G dot of J0 lower star of Y. Right, the sheaf F has somehow come into this churn M. So there's no sheaf anymore. It's only the class of the space Y, which is of course churn M on G dot of any linearly equivalent divisor. So I'll write this as J infinity of M infinity. But M infinity is reducible, so I'll get two terms. I'll get churn M G dot of K lower star of P of n plus O plus L lower star of Y tilde. And now I'll split up. into two terms, and I'll notice that that's by again projection formula type thing is K lower star churn on P of n plus O of K upper star or G dot plus L lower star of churn Y tilde of L upper star or G dot. I mean, formally it's this, but in fact what I just argued is that this element is 0 in the growth and group. It's an exact sequence of vector bundle. So this term is not there at all. I'm only left with this term, which is now computing churn on a projective bundle of exactly the type we had earlier of some sheaf.
Because that is F-bar upper star.
Exactly. So this is just already we know growth and Riemann-Roch here. So I can write a formula. So this is, let me carry on. This is just K lower star of churn P of n plus O of F bar lower star F. Now here I had a complex, but this complex resolved a particular sheaf, so I'll take that sheaf instead. And this is of course K lower star of F bar lower star of dot on X n inverse churn XF, because the embedding of F bar of X into P of n plus O is exactly like the embedding we had earlier, except the notation was E there instead of N. It's the same thing. So we already proved the theorem, and therefore Riemann-Roch there gives me this. Now, I erased that diagram unfortunately. Okay, so I had Q M to Y cross P1 to Y, the composition. Then this equation which I got here, whatever it was, I was trying to compute this, and it was equal to this. This whole expression lives in chow star M Q, but now I can apply Q lower star and notice that Q composed with K composed with F bar is just F, and Q composed with J naught is the identity on Y. So I had J naught lower star or something equals K lower star or F bar lower star or something. Apply Q lower star to both sides. Q lower star or J naught lower star is the identity. So I'm exactly just computing churn Y of F lower star F. And on the other side, I got something. I got Todd, etc. This KF will just give me F again. F comes outside. That is the Riemann-Roch thing. Because the normal bundle of N is the same whether I take the normal bundle inside P of N plus O or inside Y. I mean, I chose it like that. So it's the same normal bundle. Okay, so this does GR. Thank you.